Well, hello. Hello, everyone. My name is Doug Picklyk. I'm the editor of HPAC Magazine, and welcome to this edition of 30 Mechanical Minutes, the free webinar series offering virtual content for real-time professionals. I'm happy to be joined once again by longtime HPAC Magazine contributing writer and hydronics industry expert, John Siegenthaler. Hi, John.
Hi, Doug. Good to see you.
Great seeing you again. Before we get started, I'd like to thank our sponsor for today's edition of 30 Mechanical Minutes, and that is Conforto HVAC, a division of Granby Industries. Conforto offers a selection of heating and cooling systems, including its AT series electric boiler, a wall-hung boiler with a microprocessor control and load managing controller. Thank you very much, Conforto, for your support today. John, thanks again for joining us. And it was great seeing you last week at the AHR Expo in Chicago.
Very good to see you as well, and a lot of activity at that expo.
Yeah, the crowds were fantastic. I think the exhibitors were pretty happy. And I know we had a little chat while we were there, and we were both a little surprised at the number of air-to-water heat pumps. It was a big show for hydronics, I think.
It was. So usually when the show's in Chicago, it is a pretty good show on hydronics, just a cold climate emphasis. I would say at least 10 new offerings of air-to-water heat pumps relative to last year's event.
Yeah, but and so that sounds like a great topic for another 30 Mechanical Minutes. But today we're talking about electric boilers, which is something we also saw quite a few of on the show floor. I had a few photos when I was there. There's just a few of the offerings. A quick slide to show. This electric boilers were a hot topic at the show this year, and thus a great time for us to be talking about it here on 30 Mechanical Minutes. So with the topic of electric boilers, John, I was hoping you could just start and basically tell us, how does a typical electric boiler work? Just what are these things?
Sure. Well, an electric boiler is a relatively simple device. You're converting electricity through some type of a resistance element, similar to the elements that you have in an electric water heater. So you're dissipating electrical energy into heat. And typically an electric boiler has a pressure vessel. It's a small vessel usually. And there could be anywhere from 1 to as many as 4 heating elements. Actually, in some of the large commercial electric boilers, we actually looked at one at the show that had, I believe, 15 different elements in the pressure vessel. And these are controlled. In the old days, they were just turned on and off with contactors. Today, most of the electric boilers control the current that goes through the element, and they do that with solid state devices called triacs. So an electric boiler, unlike a fossil fuel boiler, can basically regulate its heat output anywhere from 0 all the way to 100%. It doesn't necessarily have to do that in stages, although some boilers do that. Some boilers basically have 3 or 4 discrete stages, and basically they're using contactors to turn elements on and off. But as I say, that has kind of morphed over into solid state control today. And as you build heating capacity in a boiler, you're basically doing that by adding elements. And the elements can be 4.5 kW or 6 kW elements typically. The controls within these boilers have progressed quite a bit. Some of them can not only maintain a preset boiler outlet temperature, even though the inlet temperature varies, they can also control based on outdoor reset. So as it gets warmer outside, the water temperature coming from the boiler is reduced. And most of them also have the ability to turn on circulating pump. Sorry about the dog in the background there. And they're relatively small compared to fossil fuel boilers because they simply don't have to have all the combustion chamber and gas assemblies and so forth that a fossil fuel boiler would have.
Okay. And of course, I mean, it's an electric boiler, and it's heating with electricity. So that I know you've talked about the electrical draw that these things can have.
That's probably the biggest thing you want to take a look at with electric boilers is, any kind of an electric resistance element. It could be a toaster, it could be a little space heater, it could be an incandescent light bulb. Whatever wattage goes into that is basically converted to heat. So, just as an example here, a 15 kilowatt electric boiler, and by the way, most electric boilers will be rated in kilowatts. You can easily convert that to BTUs per hour. Just multiply kilowatts by 3,413. So a 15 kW boiler is just over 51,000 BTUs per hour. That would be high enough capacity to heat a house. And it'll be served by a single phase 240 volt circuit. And that would require almost 63 amps. If your voltage is a little bit lower, say 220 volts, the amperage would go up to about 68 amps. So you can see this is a double pole circuit breaker, a fairly good size draw on your panel. And one of the very first things you want to check if you're looking at a building and contemplating an electric boiler, what kind of electrical service do you have? Some older houses, especially houses that may have had fossil fuel heating systems, they simply didn't need to have a 200 amp service. And those were less common in houses that were built several decades ago. They might have 100 amp or 150 amp services. I don't want to say that you can't do an electric boiler with 100 amp or 150 amp, but if that panel is pretty much filled up with breakers, you've probably reached the limit. And an electrician can evaluate that for you. But in general, if you're doing new construction or adding a whole house electric boiler, and by that I mean a boiler with enough capacity to heat, let's say, a 2,500 square foot modern house, generally you want to have at least a 200 amp service. And that's especially true if you're also looking down the road at an electric vehicle charger, because they also draw high amperage. So between the electric boiler and the charger, that puts a pretty good load on the panel.
Right. Okay. And I mean, in terms of typical uses for electric boilers, I mean, anything a gas boiler can do, is that right? Like in-floor heating, baseboard, panel rad?
Absolutely. Any kind of a hydronic distribution system that you would supply with a gas-fired boiler or an oil-fired boiler, radiant floor, panel rads, baseboard, anything can be supplied by an electric boiler.
Okay.
So there's no restriction there.
Now, in terms of what are the advantages, where does an electric boiler come in? I don't know what are its features? And you gave us a list here. Maybe you can go through that.
Absolutely. So, let's look at them, advantages and disadvantages. They're very small. You can, a 15 kW electric boiler, you could sit it on the desk in front of you. So it's small, it's light compared to, let's say, a cast iron boiler of comparable size. There's no combustion, so there's no issues with fuel supply, venting, anything like that. No flue, no chimney. Doesn't generate carbon monoxide, so there's no concern on that. One of the things with fossil fuel boilers that we always have to be careful about is short cycling. We don't want to turn a fossil fuel boiler on and off like every 1 or 2 minutes. That really is not an issue at all with an electric boiler, either with contactors or with modern boilers with triacs. It's not a problem at all to turn that boiler on for a short period of time and turn it off again. They make very little sound. You may hear a very small amount of sound coming from it. It might be just the water moving through it. They can be operated on outdoor reset, so that would reduce water temperature. That would reduce your losses from piping. If you have piping going through partially conditioned spaces between where the boiler is and where the heat emitters are, outdoor reset control would reduce the water temperature, reduce those losses under part load conditions. Now, one of the major things that you can do with an electric boiler that you can't do with fossil fuel boilers is to coordinate them with time of use utility rates. And these are rates, if you're not familiar with it, essentially utilities to encourage load leveling. They're going to encourage consumers to purchase electricity during low demand periods. Typically, it's at night, sometimes on the weekends when more industrial commercial uses are down, and in the US at least major holidays. So imagine you could buy electricity for, I'm going to pick a number here, 5 cents a kilowatt hour between, let's say, 11 o'clock at night and 7 o'clock in the morning, versus maybe 20 cents a kilowatt hour during the peak demand period. You could easily set up controls that would allow that boiler to operate under the low cost electricity. I put down they're mounted outside of tanks, unlike electric heating elements. So that makes them a little easier to service. If there is an electric element that's in a tank and it does burn out, it does, you'd have to drain the tank down potentially to replace that element versus isolate the electric boiler. And in a system that has a fossil fuel boiler, it's relatively easy to bring an electric boiler in, primarily because it's small. It's a matter of just piping it in place of the fossil fuel boiler and again, ensuring that the electric service is capable of operating it. So one other thing, I didn't put it on the list here, but an electric boiler can take advantage of solar photovoltaic systems. If you're dealing with net zero houses and you have photovoltaics, some of the energy that you're producing can go directly into the boiler. If you have net metering, where any surplus electrical energy generated by the solar array would simply go back out through the meter at the same rate that you buy it at, essentially the utility becomes a battery for you. And the beauty of that is you could, in a sense, you could store kilowatt hours of energy into the grid during summer, and you could pull them back during the winter. And essentially the utility has acted as a storage device for you. And obviously you can't do that with, you can't reverse a fossil fuel boiler and create natural gas or fuel oil. So those are some unique applications. Now, the disadvantages, we've already mentioned high current draw. It's not technically a disadvantage, assuming that the service to the building has the capacity to operate the boiler. But in an older building with a small service entrance, it definitely is something you want to take a look at. The other thing, traditionally, the cost of producing heat from electricity in most markets, not all markets, but in most markets, has been higher than the cost of other options, specifically natural gas. Well, with carbon taxes and with just the changing energy markets, obviously fossil fuel prices are going up, and where you may have situations where the cost of producing energy in an electric boiler is comparable to what the cost of some fossil fuel options may be. And we like to compare those options on a dollar per million BTU basis. That's what you see at the bottom of the screen there, $ per MMBTU. To get dollars per MMBTU for an electric boiler, just take the cents you're paying for a kilowatt hour of electrical energy and multiply it by 2.93. That'll give you dollars per million BTUs. And then I've got one final comment here, this thermodynamic concept called exergy. Exergy is the idea that if we have electricity, we can do a lot of things with electricity. We can run a compressor, for example, in a heat pump, and in effect, we could get 3 or 4 times as much low-grade heat into the building using that heat pump compared to just dissipating the energy into heat. So the thermodynamic concept of exergy, ideally electric heating of any form doesn't bode well for exergy, but you don't pay for exergy. It's a valid concept and it's something we need to look at, but it doesn't necessarily overrule the advantages of an electric boiler, as we've talked about, especially when you can coordinate with utility rates and storage and so forth. So you can see the advantages here definitely outweigh the disadvantages.
Right. You know, when we talk about heat pumps, we always talk about that coefficient of performance, that COP number that, you know, ranges from 2 to 4 to 5, depending on what some of these units can do, and the temperature outside. It kind of has a bearing on its performance.
Right.
But when we look at an electric boiler, people often refer to it as a COP of 1. I think,
Exactly.
is that actually generous? Is there actually some loss?
It would depend, Doug, how you define COP, but
Yeah.
ultimately, you know, conservation of energy principle, whatever kilowatt hours go into that boiler are going to come out. Now, you may have a very small amount that comes out the jacket of the boiler. You know, it's
Yeah.
For all practical purposes, when the boiler is within the conditioned space of the building, the COP of 1 or 100% efficient conversion of the electrical energy is valid.
Yeah. Okay. You know, we kind of look at these advantages and disadvantages, and so we kind of want to know what is this product's niche? Where is its best fit?
Sure. We've used electric boilers in very low load houses in areas that have low cost electricity, or for clients that want to have photovoltaics and they want an all electric solution. We've actually got a project up in Minnesota, very cold climate. It only has a 6 kW electric boiler. It heats the entire house. And it does that with radiant floor heating in the basement and some panel radiators on the main floor. It's not a large house. It's probably about a 1,500 square foot house, but extremely well insulated. So net zero and low energy houses or condominiums, apartments, definitely are going to be a possibility. Just to relate to a situation here in New York, down in Westchester County near the city, there's a natural gas moratorium. So if a developer is building condominiums, they are going to have to go to an all-electric solution.
Right.
And an electric boiler could come into that picture. Another project where we used an electric boiler, it's kind of an interesting twist. We had a client that had, they were living in a what we call a municipal electric zone, or a muni. And this is where there's a local utility, and typically the cost of energy is fairly low. At the time, it was literally 2 or 3 cents a kilowatt hour. And they were building a new house, and they asked the question, why not just put electric baseboard in versus do a hydronic system? Well, the hydronic system gives you flexibility. You can use an electric boiler as the heat source for now, and down the road you might use something else. The hydronic distribution system is open to almost any kind of a situation. So electric boilers definitely have a niche. We like to use them also as backup to air-to-water heat pumps, or even geothermal water-to-water heat pumps, but especially air-to-water. And actually, our next slide there, Doug, shows an example of that.
Yeah, this was a system that you've incorporated. Yeah, tell us, walk us through this one.
Yeah, and you'll see in the upper left there's an air-to-water heat pump system. This is actually a research project that is being done up in a very cold area in northern Maine. And they are looking at off-peak rate structures, and what they want to do is to grab off-peak energy when it's available. It's kind of a unique situation. They actually have a lot of wind turbines, and when they have a strong wind event, the local utility actually has more energy than it needs. So they're literally looking for ways to dump some of that capacity or some of that generation without curtailing operation of the wind turbines. So I've actually been told that at some times they actually have negative utility rates, which means the utility would pay you to take this energy. So the heat pump is, it's a special heat pump. It's a prototype unit that can actually generate fairly high water temperatures, about 175 degree Fahrenheit water. That's not common. Most air-to-water heat pumps are limited to about 130 degrees for reasonable performance. So yes, they can be tied into thermal storage, but they really can't get the temperature as high as an electric boiler. An electric boiler could easily do 180 degree Fahrenheit, and depending on manufacturer and what safety controls are in the boiler, they might be configurable to up to about 200 degrees. In this schematic, you'll see the heat pump and the electric boiler are just piped in parallel, and that enables either heat source or both heat sources to operate at the same time. So if the heat pump wasn't able to keep up with the load, or if the heat pump was down for service, the electric boiler could come on automatically. And what's going on with the rest of the system, you see the tanks down at the bottom and some of the piping. The controls in this system are designed to actually charge those thermal storage tanks up when this low-cost electricity is available, and then discharge those tanks back into the header and ultimately across where you see the hydraulic separator to the heat distribution system in the house. So the system is actually set up so energy can either go into thermal storage from either heat source, or it could go directly to the load. But I put it in here as an example of how an electric boiler can easily be piped in parallel with an air-to-water heat pump and serve as supplemental heat if it gets very cold out. And some of these heat pumps can function down to, let's say, in Fahrenheit, about -10, -12 degrees Fahrenheit. But there are locations, including where I live, where occasionally it might get colder than that. And under those conditions, the heat output from the heat pump is pretty low. It's not going to be enough to heat the house. So the electric boiler would come on. In fact, some of the heat pumps can automatically signal the electric boiler to come on, and its circulator would turn on, and you can see here it would just inject heat at that point. So for supplemental heating or backup heating, heat pumps are much more complicated than electric boilers in terms of controls and sensors and so forth. And I would say, in all honesty, there's a better chance that the heat pump could go down for some service requirement compared to the downtime on an electric boiler. So we like to build electric boilers into the system as a backup to make sure that the building has heat if the service is required on the heat pump, and especially in remote locations where that service may not be 2 hours away, it might be 2 days away or a week away, especially if some part is needed. So electric boiler is an ideal and relatively low cost option compared to, let's say, putting a fossil fuel boiler in there as a backup. And especially if the project is if the project goal is to be an all electric system, this is a really good combination.
Okay, we have a number of questions here. So I think let's jump right to those. And okay, someone's asking, are electric boilers potable safe?
I would say in general, no. They're not really built as electric water heaters. Now, there are tankless electric water heaters, same principle, but they go through a different NSF certification process compared to a device that's designed for space heating. I would check with the manufacturers. I don't want to rule out that some manufacturer may have a unit that is rated for both potable water heating and hydronic space heating, but in general, those are two separate categories, and there would be separate requirements to get a potable rating on the unit.
Yeah. Walter asks, is there better than one-to-one efficiency technology? Well, that's basically the heat pump technology.
Yeah, no, there's no way to fool a kilowatt hour into being more than a kilowatt hour. And that's true not only with electric boilers, anything. If you put a kilowatt hour into it, a kilowatt hour comes out. So there's no way that any electric boiler or any other electric resistance heating device can create more heat than what the input is.
Someone is asking, they have a 6.72 kilowatt hour solar system, 14 panels. For heating, how many more panels would I need? I think that's a tough question to answer.
Yeah, you'd have to run numbers. And I would tell you to, first of all, check if you have net metering. Look at what your solar system puts out on an annual basis. That would tell you, these are how many kilowatt hours this photovoltaic system puts out. And you could kind of extrapolate from there if you wanted to add more panels to cover your heating. But again, net metering is an ideal scenario, and I'm sure it would be possible to quantify that question and figure out how many more panels you would need. Off the top of my head, I honestly can't tell you.
Right. You mentioned that trial that you're doing with the special heat pump that that's putting out 175. A couple of people are asking what kind of refrigerant.
Sure. Yeah, that's a product that is actually a cascading refrigerant system. So what it is, it's an R410A refrigerant system in an outdoor heat pump unit. And the refrigerant, the 410A, comes in and it goes through into the evaporator of another heat pump circuit, which is running on R134A. So it's kind of one hands it off to the other, so to speak. And in the process, the temperature is boosted. So they're using one heat pump cycle to capture very low grade ambient heat outside. And then they're using the indoor heat pump cycle to amplify that heat to a higher temperature. Now, you want to keep in mind, as you go to higher temperatures, there are thermodynamic limits on what you can get for efficiency. So the COPs are not necessarily as high as a heat pump that isn't forcing water temperatures up to that range, but it is possible, and you're going to see more of it from heat pumps with CO2 refrigerant and also with propane eventually. I don't think Canada or the US has regulations set exactly on how propane can be used as a refrigerant. It is a flammable refrigerant. I do think you will see it in the future. I honestly don't know if that's 3 years away or 10 years away, but you eventually will see heat pumps that can get to those higher temperatures.
Yeah. Okay. Someone just threw out a comment here. If we had any, or you had any comment on electric boilers, simply, I guess what they call extending the tailpipe, and that has to do with where your electricity source is coming from. And if it's a natural gas plant that's creating that electricity, you're really just creating carbon emissions on a larger scale. And that's
absolutely, they're correct. Burning natural gas to create electricity is roughly about a 33% process. And there is transmission line loss. No argument there at all. That is true. And that's kind of reflected in the exergy concept there. So, from a global carbon capture standpoint, no form of electric resistance heating, whether it's a boiler or a space heater, anything, they're not ideal from a pure thermodynamic standpoint or from the standpoint of trying to minimize any kind of emissions, but they do solve problems. So they are they're a valid product in the market by all means.
Yeah. Someone did ask what type of device can control this type of setup, that air to water heat pump and electric boiler.
Well, it depends on the products. You're going to find some heat pumps can actually signal the electric boiler with just a contact closure to turn on. They will measure the water temperature they're producing, and if necessary, they will signal the electric boiler to operate. Most, I'll say, state-of-the-art heat pumps have that capability today. They have a way to signal an auxiliary device, be it an electric boiler or some other type of device, that'll respond to just a contact closure.
Okay.
And if they don't, that could be done with a simple 2-stage set point control or 2-stage outdoor reset control, where the first stage would operate the heat pump and constantly monitor the temperature, and if necessary, the second stage would turn on to bring the electric boiler online.
Okay, this is going to be the final question because we are out of time. Someone asked about water quality issues. And I mean, I did have a question about maintenance too. I don't know if that's What kind of maintenance is there to these units?
Well, minimal maintenance. The water quality is probably the key to minimal maintenance. And the manufacturers are likely to have a water quality specification in their manual. You want to check that out. As is true with any kind of a hydronic system, I'd recommend demineralizing the water. The hydronics industry has gotten more serious over the last few years about water quality. And demineralized water. And there are other procedures. For example, if you're doing a system with copper tubing in it, especially if it's being soldered or if it's an older system you're retrofitting, I would recommend washing that system. And there are several products on the market that are, I'll call them hydronic detergents. They basically go through and they internally clean the system. They're biodegradable. You can flush them down the drain. And then adding either you can buy demineralized water or you can demineralize on site. And again, there are a number of companies that offer demineralization systems. Demineralizing the water is going to take out the calcium and the magnesium, the salts that are typically in groundwater. You don't want to use softened water. Softened water is going to have sodium and any kind of a mineral deposit, any kind of a mineral in the water could ultimately deposit not only on an electric boiler, it could deposit on your heat emitters, it could deposit on fossil fuel boilers. There's nothing about an electric boiler that makes it more vulnerable than any other heat source operating at similar temperatures. So water quality, first thing, check the manufacturer's IO, installation operation manual. And there are other things. I know Calefi puts out some publications on water quality, and you can find other resources online. But pay attention to water quality in any hydronic system. That is going to be the key to a long life on these products.
Yeah. I have to apologize. I did see a lot of people were talking in the chat, but some people were answering other people's questions. So I think that's great. So thank you to everyone. Want to once again thank our sponsor for today, and that is Conforto, providers of heating and cooling solutions. And more can be found out about Conforto at confortohvac.com. That's their website, confortohvac.com. John, thank you again for participating in today's 30 Mechanical Minutes.
Sure.
It's always a pleasure. And before we go, I want to remind everybody about the CMPX show. There we go, CMPX, March 20th to 22nd here in Toronto. You're not going to want to miss it. Let everyone know that we're looking to host a live 30 Mechanical Minutes on the show floor with John, because I know, John, you're going to be up here in Toronto for the show.
I am. I look forward to it. It's a great show. If you've not been to it, I'll be doing a presentation on the 21st in the morning. And specifically, it'll be on adding air-to-water heat pumps to existing hydronic systems. And then, as Doug was saying, we'll follow up with 30 Mechanical Minutes in the afternoon.
That's what we're looking forward to. So check it out. Stay tuned for more information on that. Also, John, you'll be joining us again this September 12th, 2024. The Modern Hydronics Summit comes back to Toronto. We're just north of Toronto in Vaughan. Registrations will be happening soon. So again, keep on the lookout for that. If you're a hydronics person, this is where you're going to want to be on September 12th. And finally, just a reminder of the HPAC Magazine Sweet Heat Contest, sponsored by MCO. This year, 2024, there's going to be 3 prizes. We added a category. There's commercial hydronics installations, and then 2 in the residential category, 1 for new builds, and then 1 for retrofits. So you're taking pictures of those great installations you're doing. Be sure to send them in, enter this contest. There'll be more details coming out very soon on how you can get involved. And John, I have to thank you for participating in the years past in the judging and announcing the winners at our summits. So
yeah, some really nice systems.
we encourage people to get involved. So, and that's it. So John, thank you. Thank you everyone who's been watching. And until next time, that's it for this
Okay.
edition of 30 Mechanical Minutes.
Take care.